it's a real pleasure for me to have this presentation by Oliver Gröning here. He's one of these guys that like to travel long distances to come to work, maybe because he needs time to think about the many things he's doing during his long days that keeps him busy, sometimes maybe even at night, to understand what the measurements are, what the theories tell. Oliver did his primary schools in Gerlafingen, that's close to Solothurn, right? And you are still kind of connected to these areas. And did his mathematical studies and his PhD at University of Fribourg, together with in the group of Louis Schlappach. Then came here, actually not really here, mostly Thun, because the team was doing the first experiments there for quite a long time, and moved then 4 years ago, is almost?
It's now soon 5 years ago.
5 years. Well, I know it took longer than expected to do the transition, because moving such complex experimental setups was not an easy task. And when I look at what was done during this time, I'm always impressed, because it's not only about graphene, it's about all kind of carbon compounds and even more complex structures. And it's not only about basic science, which is fascinating, but it's also about connections to companies that Oliver was involved, Thales being one of them, Philips Research another one, related to these various activities with graphene nanotubes for emitters, for novel X-ray sources, but also recently more on novel dynamic lithography systems down to the nanoscale, called NanoStencil. That is also a project that has started quite some time ago, that is now getting more and more momentum, and I'm always impressed to see all these various experimental activities, as well as then the connections to theory, to modeling, because I think this is very exemplary, kind of a very special example that you can do modeling and electronic nanostructures and synthesis of novel materials at surfaces all together, and look from these complex, various different aspects to it. So tight binding modeling of the electronic and magnetic structures is one thing that you are pushing together with your colleagues. I'm actually standing here because the lab leader, Roman Fasel, has what is very common these days. He got the flu. I had it last week, so I'm happy to be here. And so I'm looking forward to your presentation on material science at the atomic limit, and learn more about the challenges that you have and you're facing. Thank you.
Well, thank you so much, John, for the introduction, and thank to all of you for actually being here. It's actually a great pleasure to talk to you a little bit of our work in the laboratory that has been going on over the last 10 years. And as it is often the case, if you have to give a title 4 months in advance, it's rather a non-descriptive title. So material science at the atomic limit, to some extent, doesn't make much sense, because material science finally, at the ultimate level, is always concerned with the atomic limit. However, the background image gives a little bit away to what I will point to in this presentation, and this is actually materials at the mesoscopic scale. So where we are positioned between two extreme worlds, if you want to say so. On one hand, the very small, what we know from chemical compounds, where we have the characteristics that minute little changes on the atomic level really change properties a lot. So we have here two chemical compounds, adrenaline, where my adrenaline level maybe is the highest in this room at the moment, and on the other hand, a similar yet differently functionalized compound, aspirin, of course having a different function. And this extreme sensitivity on atomic modification, of course, can go on. It can even be expressed in two chiral molecules, so molecules which have the same stoichiometry, the same composition, but also the same topology. The binding structure is exactly the same, but the difference is they are left and right-handed version of each other. And there's, of course, the famous yet sad story of thalidomide, which is Contergan in its commercial name, where the right-handed version of the molecule is a sedative which cannot be overdosed, so this was very attractive to be a medicament. But on the other hand, the left-handed version was actually harmful during pregnancy because it caused very severe at the extremities of the fetus, very strong deformations. But if we think about, so this is of course a very interesting property. If you change materials down to this level and you have such strong modifications of the property. However, to talk about materials in the classical sense is difficult. So what would be a base material here? If we go to these kind of structures, this is much more familiar. We have kind of a base material, steel in this case, where we have a set of more or less size and shape independent properties. So specific conductivity, elastic modulus, and so on. And these are then exploited in different shapes. And so what I'd like to show you today is actually structures where these two worlds meet. So where we can identify a base material which is modified in different structures, and where modification on the atomic level really make very significant differences in the physical properties. The most, or for me, one of the most exemplary structures in this sense is the C60 molecule. So we are definitely still on the molecular level, 60 carbon atoms, and still it has a different flavors compared to the other chemical compounds that I just showed you. So it's an allotrope of carbon, which means it is a pure form of carbon, and we have all the 60 carbon atoms actually in equivalent sites. We have pentagons, which are required to close the structures, so the curvature of the structures comes actually from the pentagons, and then we have still the hexagons in there. So the structure is of icosahedral type, so in the corners of the icosahedra, we would have actually the 12 pentagons which make up this structure. It is a compound which is used today. Actually, it is a very good electron acceptor, and in organic electronics, it is used in this function. So it is used as an electron acceptor, as the N-type conducting channel, for example, in organic photovoltaic cells, but it's also used as a high-resolution deep UV photoresist, and also in cosmetics you will find it as an antioxidant. So for a physicist like me, this is like a little capacitor, and what chemists can do, and this is really amazing, they can couple this little capacitor, for example, to an optic active center, like here it is porphyrin. And then you can study excitation, so photoexcitation, electron-hole pair generation, electron transfer, recombination, and you can, of course, look at all these processes in great detail. However, the C60 is not a solitaire, it is not just there, but it is actually one member of a large family of different structures. And this becomes apparent if we go to higher structures, for example, the C240, C510, and finally here to a very large structure, the C960. And here you might agree with me that we can say that there is a base material which is at the basis of all these structures, and this is graphene. So all these structures have in common that their curvature is induced by 12 pentagons, and the rest is the usual graphene structure, so the honeycomb network that we know so well from graphene. So the buzzword has been there, graphene. This will be the base material I want to talk to you about. And it's, of course, the material of the moment. There's certainly a little bit of hype around it. That's definitely true, but this is not completely unjustified. So if you look at the physical properties of the material, it is really outstanding. always with the caution that a nanomaterial has different or more exciting or higher quality values than really a real bulk material, like, for example, steel. But if we compare young modulus with tungsten carbide or tensile strength with Kevlar, we really see the great mechanical potential this material has. But also regarding electron mobility, which is an important figure of merit for semiconductor physics, we see that even at room temperature, extremely high electron mobilities can be achieved if we compare them to more classical semiconductors. Resistivity, heat conductance, but also specific surface area are all extreme for this material. But what I like to concentrate in my presentation is actually the electronic properties. And being a solid-state physicist, I cannot talk about electronic properties without talking about electronic band structure. What is a band structure? Actually, it's something very simple. It's just a relation between kinetic energy and momentum. And this is, of course, something very important if you want to understand the dynamics of any object that we are concerned about. So first, let's start with the classical particle. So we have, of course, the well-known relations that we have learned in high school between momentum, velocity, and kinetic energy, which is that the energy is actually the square of the momentum, and we have a proportionality factor, which is the mass. So the band structure would actually be a parabola. I plot now here in one dimension. Of course, momentum would be a three-dimensional quantity, but reduced to one dimension, we would have the momentum here, and the parabola would express then the possible kinetic states of this particle being a parabola. This is not completely true, because we know that these Newton relations, they're actually not the correct one, but we have to take the relativistic energy-momentum relation where the rest mass comes into play. So if we have a particle or an object which moves very, very fast, so where this quantity becomes negligible, then we will have a linear relation between momentum and energy. And the band structure, so to speak, looks then something like this. So we have still a parabolic part, which is at low velocities, at low momentum, but at high velocities, at high momentum, approaching speed of light, we then have an independent or a linear relation between the kinetic energy and the momentum. This becomes extreme in the case of a photon, where a photon has only one choice to move. It can only move with the speed of light. And then we have a fully linear dependency between momentum and energy. And this relation, so this parabola actually only expresses all the possible states that this particle can take. So you all sit in the chair, so you are all actually in the ground state, you don't move in this frame of reference, so you have lowest kinetic energy and no momentum. I'm moving a little bit around, so I occupy different states down here in this parabola. Now if we go to graphene, this was actually calculated, the electronic structure of graphene was calculated in a tight binding picture a long time ago by Wallace in the 1940s. And calculating graphite, he came across, as a first step, across graphene, so the single layer of carbon that we would find also in graphite. Of course, you need to have the sp2 hybridization, so this is actually the base function that you use. And then what he found by his calculations was very interesting. If you approach the charge neutrality point, so if you look at neutral graphene, you will have that the density of electronic states actually goes to 0 at this point. So if you have electron deficient graphene, you will have a finite density of states at the conduction level of energy. And also, if you go into the n-doped regime, you will have a finite electron density. But right at the charge neutrality point, where we have neutral graphene, you have a 0 density of state. He also calculated the band structure, which looks a little bit different from what I've just been showing you. This is, of course, because we have a two-dimensional relation, so we have a two-dimensional momentum in the plane of graphene, One can express this now a little bit more colorful nowadays. So this is the dispersion relation. We have the momentum in the x and y direction and the energy, which is now color-coded, which is still very abstract here. So of course, rendering this in 3 dimensions becomes a little bit more visual, but maybe not simpler. However, what you see now here is, again, the energy in the vertical axis. You have the momentum in the plane. And now if you compare this with what I have shown you, well, this is pretty different. And now what are we interested in? We are interested in the electrons which make up the conduction in graphene. And these electrons, they live actually at these points here or very close to it. So where we have this plane, this pink plane, which is put here in. And so we need to look a little bit more closer at these points. And what you see is that these are cone-like structures. So this looks like this. Again, we have here a massive particle, as we would be. We have a parabolic relation between energy and momentum. But here what we have is actually, we have these cone-like structures with a linear dispersion. So the particles, the electrons in graphene, they do not behave like massive particles, but they behave rather like photons. They have a relation between energy and velocity, which is independent. So they move at no matter which energy at the same velocity, which is the Fermi velocity. And this is, again, similar to ultra-relativistic particles, like, for example, electrons. But you see also there is something additional. So you see here this particle is just black. It has no other property than moving around. But you see that the electron, it has a further property, and this is the spin. So this is the kind of angular momentum intrinsic to the electron. And at very high speeds, something happens. This spin aligns itself with the motion of direction. So if we now think about a fundamental process in conduction, which is backscattering, so we have an electron which moves in our material, it comes to a defect or to a potential barrier and is backscattered. So what does this mean? So it's actually like this ping pong ball, which has a momentum, and as it is backscattered from the floor, the momentum is reversed by 180 degrees, and the particle turns back. What does it mean now in this diagram for the electron? It means going from this state, which is actually a left-moving state, it would need to go to a state over here. So this would be a complete reverse backscattering. This is very simple for the ping pong ball. It just needs to inverse the momentum. But for the electron at ultra-relativistic speeds, it gets more complex because the spin, which is pointing in this direction, on this side, it needs to point in the other direction. So backscattering must be also combined with spin flip. And this requires very stringent requirements onto the scattering defect. And if we go to graphene, which is represented here, we see that the ball also has some kind of strange property. So it's a green and red ball. What does this mean? Well, if we look at the real part of the wave function, so I try to talk you through here, of a right-moving electron, it looks something like this. A little bit strange. This stripe-like structure means actually that the movement is in this plane. And if we now compare it with the real part of the wave function of an electron moving in the other direction, this looks different. And what I would like to point you to is actually the unit cell here, in which we have 2 atoms. So this is the basic building block of the graphene, these 2 atoms. And for the right-moving electron, they have the same sign. So they have the same parity. But for the back-going, for the left-moving electron, you see they have changed the sign. So one is positive, the other one is negative. And this property of the sign of the wave function on the unit cell, this is called a pseudospin. So this is a property which is similar to the spin of the electron, but here it is a spatial property of the wave function. And this makes backscattering actually very difficult, because again, it is not sufficient just to reverse the momentum. At the same time, you need to reverse the parity of the wave function on the sublattice. And again, this makes backscattering very unlikely in weak potentials. All these features, this very specific photon-like or massless Dirac fermion-like dispersion, leads to a range of different physical properties. So I already told you it's a zero bandgap semiconductor. So it has a vanishing density of states at the Fermi level, but it has no real gap. Backscattering is strongly suppressed. This leads to high carrier mobility. Actually, the combination of these two properties leads to high carrier mobility. Suppression of backscattering also leads to very large ballistic transport lengths of several hundred nanometers at room temperature. Optical properties are quite exciting. So you have a wavelength-independent adsorption in the infrared visible range. You have also saturable absorption, which means the absorption is highly intensity dependent. You can have a gate control over the adsorption, and then more exotic features like fractional quantum Hall effect and Klein tunneling. So this is a set of really very specific and very unusual physical properties with regard to the electron transport. The fascinating thing is now that the properties of these base materials can be modified in bringing this material to a vast kind or a vast number of different structures. So this is kind of a little phase diagram for pure carbon, where you have zero-dimensional structures like the C60, you have 1, 2, or then 3-dimensional structures where you have here the graphite, here the graphene, but you have all kinds of different intermediate structures. And this diagram is not just science fiction. These materials really exist. So I've shown you the C60 as a ball and stick model. If we go back actually a long time to our beginnings at Empa, Pascal is smiling a lot. He knows how I like this system so much. One of the first experiments, we actually put C60 on tantalum disulfide. Tantalum disulfide has a special property. It has a superstructure. So what you see here is not exactly the atomic structure, but it is a superstructure imposed onto the atomic structure. It's a so-called charge density wave. So it's a structure which is dependent actually on the electronic property and also on the charge which is on this material. And we wanted to use the property as electron acceptor of the C60 to modify the charge state of the tantalum disulfide in order to induce or to see how this pattern would change. Well, we could look below this C60 layer. However, we didn't really find any correlation, and you see the result is actually unpublished. But what we saw is, if we look very hard, so here you see actually 3 C60s in this island, and they look all a little bit different. So they look a little bit like donuts, these two, and this here like kind of a 2-bell donut-like structure. And if we know that we are looking here at the lowest unoccupied molecular orbital, one can calculate that the highest electron density is actually on the hexagons, and that the pentagons, they will show up as little holes in the charge density. So we can actually figure out what the rotation angle of this C60 is in the plane. So this would be the ball and stick representation, and this would be a little simple sketch of the electronic structure, which we measure with the scanning tunneling microscope, which is not just a microscope, but which is also a spectrometer. We have access to the electronic properties of the material. And if we look a little bit further, so again, here we have this donut-like structure, and of course, what we would like to know, well, when does the pattern repeat? And well, it seems that if you go to here, where this looks very, very similar, so this seems to be the translation vector of the periodicity of our structure. But if we now make a stroboscopic image, so we jump actually in each image from here to here, so we reposition this molecule to this position, then we will see that this is not yet the unit cell that we see. But if we do these jumps, then we see it looks as if these molecules are really rotating. They are not really rotating because we are jumping from one position to the other, and we are always looking kind of the same position. What really happens is, as we move along this sequence of different C60 molecules, their registry with the substrate is always a little bit different. And this different registry with the substrate is like as if we would move very slightly the substrate with regard to the molecule, and this rotates. However, these are very complicated structures. We could never really figure out how really this rotation is linked with this position on the substrate. But it is actually a topic which has remained with our laboratory till today. So what is the interaction of molecules with surfaces? If we go further, another molecule, so kind of the flat equivalent of the C60, also those exist. Klaus Müllen at the MP of Mainz actually is a specialist in synthesizing them. And I would say Pascal is the great specialist on looking at them on the surface. So you see here again STM images of a stepped gold surface, and you can see the molecules here biting a little bit into the edges of this stepped surface. And one can really see that they seem to like very specific positions, so they're all oriented the same way. And of course, at that time, even today, theory here from the group in Liverpool actually is very important to give us the energetics and also to compare simulated STM images out of DFT calculation with the measurement ones. So here we have different position. It's actually here the atomic step with a kink site, and this is the ideal energetic position of the molecule, which we find here energetically more stable as compared to other positions. Now, carbon nanotubes, I don't need to convince you that they exist. Here we have also, again, STM images. I will talk a little bit more about those guys. More recently, we have also, of course, due to a breakthrough here at Empa, the possibility to access atomically precise carbon nanoribbons. So again, a flat version, if you want to, if you allow me the simplification, of the carbon nanotube in the plane. And the rationale or the systematic of producing these atomically precise structures of 1 nanometer or a little bit, or having different structures, how do you produce them? You start with a molecular precursor. So this is kind of bottom-up chemical synthesis. You start with this dibromobiantyl molecule. You put it onto a surface. You heat a little bit so that these bromine groups, they cleave off. You have then here a radical which is formed, and these radicals can polymerize to a chain. You see this chain here. Actually, this is the STM image. This is the simulation. And in the second temperature step, you take away the hydrogen, which is still here and here, which makes this kind of zigzag flipping of this chain, and then you get this graphene-like nanoribbon. This can be also put into two-dimensional structures if you take the appropriate precursor. So this is not a precursor which has two linking positions, like a train. If you have just a linking position in front and at the back of the wagon, you would just make a linear chain. But here you have 6 iodine-occupied positions where you can then link together this molecule to form this kind of porous graphene. You can even go higher. You can have then more hybrid structures where such type of carbon nanoribbons, graphene nanoribbons, can fuse together in order to form more complex junction-like structures. And here you see not STM, but actually atomic force microscopy images of ultimate resolution. So you really see here that you can resolve it's not really a bond that you see, but it looks like a bond. And this requires that you can functionalize your tip with a CO molecule, and you can then measure the frequency shift of a tuning fork by the interaction of the CO molecule with the substrate. So this is kind of an achievement that Thomas, Hayo, and with the help of Shigeki from Basel was achieved last year in our laboratory. So if we think now going to the exploitation of such materials, we are actually confronted with the same challenges as all materials face. So first of all, we need to achieve appropriate function. We need to be able to have an appropriate synthesis of the material, and at the end, we also need to integrate these materials in a device. All of these 3 domains, of course, then are subdivided in even more challenges. But I'd like to go a little bit through these different areas, always with a little bit of flavor of showing you also how our laboratory contributes to these different areas. So first of all, function. How is function modified by structure? And this I'd like to show you on the classic example of the carbon nanotubes. So here we have actually taken from the image you have seen before, we have 3 kind of different carbon nanotube structures, which are labeled by this so-called chiral index, which are 2 numbers. And these 2 numbers, they do nothing else but describe within the plane of graphene the vector which goes from one atomic position around the circumference back to the origin again. So the longer this vector, the wider the carbon nanotube is, the more we go away from a high symmetry direction, the more this kind of chirality will be expressed. Then you can describe with this chiral vector, which is then actually expressed in the 2 base vectors of the graphene lattice. Then you can describe actually all the geometrical parameters. But what about the electronic structure now, if we have this? So first of all, let's look here at a so-called armchair carbon nanotube. Armchair, because if you go around the circumference, the bonding structure looks like an armchair in this motif here. And let's imagine that we are an electron which is living on this carbon nanotube. And this electron, it would be a flatlander. It would know nothing about the 3rd dimension. It can only move within the plane of graphene. First of all, we can look down just this infinitely long carbon nanotube, and it will look to us as if we are on graphene. Nothing special happens. But if we go further, if we look now in the other direction, if we look around the circumference, what we will see, we will actually look around the circumference and see our back again. So it would be like looking at many replicas of ourselves in a periodic arrangement where the distance is the length of the circumference. So it's a little bit like in the song of Manimatu at the hairdresser where he's sitting between 2 mirrors and he sees an infinite kind of series of images of himself. And this has a special consequence. The consequence is that the wave function must form a closed vibration, if you want to call it like this, around the circumference. So we can have different wavelengths, but the requirement is that these wavelengths are always integer fractions of the circumference. So even the wavelength circumference divided by 0 is possible. And if we think what is the momentum, well, the momentum is nothing else than this value here. It's actually the inverse wavelength. And as this wavelength, this is the circumference, as this is quantized, we get a quantization, so this is an integer number, we get a quantization of the momentum in this direction. In the axial direction, nothing happens. It can move freely. So if we go back again into the dispersion relation of graphene, it means that here we have all possible states which are accessible to the electrons. In the carbon nanotubes, they are restricted. So all states are still accessible in the axial direction, but in the circumferential direction, we have a quantization, and only these green lines are still now the allowed states. So the band structure now is actually cutting out these stripes out of the dispersion relation, gluing them together, so to speak, and then we would see this kind of regime. Again, we have this linear dispersion here, so also the electrons here behave like photons, but we have a non-vanishing density of states. So this is a metallic structure. We have no gap. Now if we go further and we change a little bit, we keep the orientation of the graphene lattice, but we now change a different axial direction. Now the quantization takes place in this direction, and now things are different. So whereas before we always hit these points, and these are those kind of cone points, so we always will have a metallic feature here because we are cutting through this so-called Dirac point. However, here we miss them. So in this case, actually what we have is these allowed states, they now have a gap. And these carbon nanotubes are actually semiconducting. But this is not necessarily the case. These quantizations can be adapted such that we again hit those points, and then we have metallic ones. So minute differences, you might imagine that this is not a very big difference in diameter, completely changes the electronic characteristics of these materials. Once we have such a structure, of course, we can use it in a device. This is actually the investigation on how transistors behave made out of semiconducting carbon nanotubes, single-wall carbon nanotubes, when the channel length becomes very, very small. And what one can see that independent or almost independent of this channel length, we have very, very, very good field effect transistor behavior. So this is the gate voltage, which is here below. With this gate voltage, the conduction through the carbon nanotube is controlled. And what you can see is that we get actually up in the microampere range. So we can switch currents up to about 10 microamps. And if you calculate the current density, this is about 100 million ampere per square centimeter. So these are huge currents for this 1 nanometer thick structures. So this is then the equivalent diagram, how such a device would look like. We have the carbon nanotube, we have two contacts where the current is flowing, and we have a capacity coupled gate electrodes where we are changing the electronic levels of the carbon nanotube by this gate voltage and thereby controlling the current which runs through here. What we wanted to do actually when we looked at carbon nanotubes with the STM was to have a little bit a different device structure, something which looks like this. Looks similar, with the change that we don't have ohmic contacts, but we have tunnel contacts, and we have a very, very small channel. And the idea was to have here a quantum system. So we weren't happy just with the quantization around the circumference of the carbon nanotube, but we wanted also to achieve quantization in this direction. Well, how can this be done? Of course, this will be very difficult at small distances. Well, these tunnel junctions, we wanted to produce them by defects. So we irradiated this carbon nanotube sitting on a gold substrate with 200 eV argon ions and produced this defect. And then we took the STM, we went into spectroscopy mode, so we measured as a function of energy the electron density, which is the differential conductance, and then really between these defects, what we observed is this type of structure. So 2 antinodes, 3 antinodes, 4 antinodes, 5, 6, and so on. And this, of course, is really the characteristics of standing waves of electrons that we have in this little resonator. And the energy separation follows actually a very, very simple law. So if we have here about 12 nanometer of separation, 1.8 eV divided by 12 nanometers, we will really have 0.15 electron volt separation of the levels. So this actually really works. Well, the device to make out of it, to put a gate onto it and to measure transport, this of course is very difficult and we didn't really do this. However, we went further because what we have here is actually again electron scattering. So these walls, so these are kind of particle in a box analogs, these defects, they act as scattering centers. So the electron is actually reflected at this point, and forms a standing wave in these two regions. And by looking into more details of the vibrations of the standing waves, we don't only see these kind of strong antinode patterns that you have just seen, but we can actually make a Fourier transform, and then we see these kind of maps. So this is real space, position, energy, electron density as a color, the Fourier transform, and then we have these kind of patterns. And what are these patterns? These patterns show us scattering events. So this is a sketch of the dispersion relation. Again, we have these conical dispersion relations. We have the pseudo-spin here. And what we see is scattering between these two states. And in the Fourier transform, we don't see this. We only see the exchange momentum. And the exchange momentum is actually these vectors. So if we plot them back, we have this kind of half-X structure that you see here. There are different scattering possibilities, for example, from this branch to this branch. If we plot this, we will have a negatively sloped branch. And we have also, for example, this scattering event, which will produce an upsloped branch. And we have many, many of those scattering possibilities. And if we just forget everything about the spin, the pseudospin of this structure, and take a Fabry-Perot model, and look at the standing waves which can be produced in such a structure for this chirality of the tube, this would be the outcome. So many X-type branches, a very strong one here. And what you can see, well, we don't have all of them in the measurements. And the question whether a branch shows up or is not there is a question of symmetry of the defect and conservation of the pseudospin or not. So whether this pseudospin must be conserved or not, some of these scattering events are allowed or they are not. And today I would say that we have a very good understanding what happens here. Well, if we go back, you see that this branch here, this is actually this type of scattering event. And you see it's a spin flip. So the pseudospin must flip in this scattering event. But I've told you before that actually the reason why the pseudospin is not easy to flip is a reason for the suppression of backscattering. Well, the pseudospin is a property of this sublattice. And if we have a defect which makes a sublattice type of defect, so where we are changing one of these atom types, then we can break the pseudospin conservation, and this scattering becomes possible, and then we have this branch which shows up. So if we go now with these properties to all possible, so the periodic table of the carbon nanotubes, we have different types. We have the semiconducting type, so it's difficult to read. So here we have the different chiral indexes. We have the semi-metallic ones, which are the light blue ones, and the metallic tubes. And of course, if we want to exploit this material, it would be very nice to have one specific type of carbon nanotubes. But in the production, in the synthesis, usually we can tune the diameter, but usually we will produce actually a mixture of many of them. It's already a challenge actually to investigate which type of carbon nanotubes that we have. And one way to figure out is actually to do a resonant fluorescence measurement. So you do a photoexcitation over the E22 gap, so the large gap between this point and this point, and you look at the de-excitation over the small gap. And if you then plot as a function of the excitation wavelength, so the blue one, and the emission wavelengths, which is the red one, if you map this emission, then you will have specific spots here for two different production types, so alcohol-derived CVD and high-pressure CO CVD. Then you will see that actually we can measure the distribution of these different species of nanotubes that we have in the produced substance. This is, of course, an important step to achieve purification. And this is a big achievement which has been done almost 10 years ago now. And today you can really buy post-deposition by ultracentrifugation separated metallic carbon nanotube and semiconducting carbon nanotube. This is done by surfactants. So these surfactants, they change the specific density of the carbon nanotubes as a function of the diameter, and by ultracentrifugation actually you have a separation. And by changing the pH, you can actually have a more specific functionalization of the metallic carbon nanotubes as opposed to the semiconducting ones, and thereby separating the semiconducting from the metallic ones. And once you have this kind of type pure material, of course then, oh, I forgot this. So this is post-deposition type sorting. Very recently, actually, there was also advances on phase pure growth of carbon nanotubes out of the catalyst used in the production. So here by a Chinese group using anorganic growth catalyst, and here in our laboratory actually using an organic precursor molecule. So this is specifically designed by the Empa-TV in Stuttgart So by dehydrogenation and closing of these bonds, which are here indicated by these lines, this molecule, which first lies almost flat onto the substrate, actually folds itself to a cap of a carbon nanotube, and then this cap is further grown by addition of carbon species due to standard CVD using, for example, ethanol. And if we look down on this cap, it looks actually like a C60, and here again you have these donuts that you have seen before. So this is simulation, and this is the STM measurement, and here then finally the zigzag tube. So if we have this material, well, we can go to integration. And the first integration is a very simple one. So you predefine, again, the field effect, the standard field effect transistor geometry. You have a source electrode, a drain electrode, an isolation layer, and you have the controlling gate electrode. And then, just by drop casting or spin coating, you deposit a network of semiconducting carbon nanotubes on it. It will be a random network, and you can actually produce, again, quite impressive transistor field effect transistor characteristics. The nice thing here is that because this is not a thin film, but kind of a spider net network, you can maintain these characteristics to very, very small bending curvature of 1 nanometer. So this is ideal for large integration, printable electronic, low cost, rather low frequency, so this is not processor-grade technology, but for signal processing, amplification for memory cells or sensors or RFID, this is a very cheap and convenient method. If we think about going to semiconductor digital electronics, well, we would like to address a single carbon nanotube in the transistor and not a network. And how to approach this? So this is a breakthrough of the IBM Watson laboratory, where site-specific deposition of carbon nanotubes has been achieved by functionalization. So by appropriate functionalization of the hafnium oxide, as opposed to the silicon oxide, and also counter-functionalization of the carbon nanotubes, they achieve deposition out of solution of the carbon nanotubes only in these trenches here. And as you go down, so this is 500 nanometer scale bar, as you go down in the width of the trenches, the carbon nanotubes start to align. It's a little bit difficult to see here, but this is then investigated here in more detail. So what you have here, it's the width of the trench, which gets smaller and smaller. They have measured the length of the nanotube in this trench and the orientation angle in the trench. And as you see, if the nanotube length exceeds by far the width of the trench, then you have an alignment. And then you can achieve really the single deposition of a single carbon nanotube in one of this trench. You can then use these trenches, which are here, put contacts onto it, and then you can really have a massively parallel integration of the single carbon nanotube transistors. And here, for example, the field effect characteristics of 7,000 devices have been measured. And you see, well, the sorting is not perfect. So all these lines here, actually, they can be metallic nanotubes, which are still present in the primary material. How far can we push this scheme of site-specific deposition of functional units? Well, what you are looking here is actually a single layer of hexagonal boron nitride on rhodium-111. This is produced by thermal decomposition of borazine. And what we have is a little lattice mismatch between the rhodium and the hexagonal boron nitride. So our substrate is hexagonal rhodium, and we put this a little bit smaller unit cell boron nitride on it, and what we will have is kind of a Mare pattern. So we have a coincidence lattice where, for example, here in this region, the nitrogen, which is green, is on top of a rhodium atom, and here actually it is in between in the hollow sites. We will have different interaction of the boron nitride single layer, which actually has the same structure with graphene, and we get then these holes, which are not holes, they are just pores, so there's a different interaction of the boron nitride to the substrate. And the distance between these pores is 3.2 nanometers. And this template can then be used to position or to assemble at very low temperature single individual molecules. And this molecule you have seen before, it's actually the precursor molecule for the porous graphene growth. And of course, we did these experiments to look whether this molecule can be assembled to larger graphene structures. But this is very difficult. And we also found out why this is difficult, because the first step that we need to achieve is the dehalogenation. So these iodine atoms, they must cleave off. But if they cleave off, we have a strong bond then to the boron nitride, which happens. And this can actually then be looked at in sequence in the STM. So here we have the intact molecule, here we have the beginning of the dehalogenation. So this iodine atom actually then is cleaved off in the next sequence, then we cleave off this, and then we cleave off this. And we are left over with this molecule where still 3 iodines are attached. And the reason why this is so stable is actually the bonding of the molecule to the substrate. So this is a little bit a disappointing news that CVD, as we are using it on metals, here on this insulator will be more difficult. However, it can then also be used for different type of molecules, here phthalocyanine, and of course the ultimate goal would be again to produce something like this. So to have a functional unit, which is here the porphyrin, to have a source and a drain contact and a controlling gate. But you might imagine that on this scale, so this is 1.5 nanometer, such a structure is very hard to produce. But sometimes you get lucky, and in the scanning tunneling microscope, you can have this type of configuration. So the drain electrode is the tip, the vacuum is one of the tunneling barrier, we have the molecule, the insulating hexagonal boron nitride is the other tunneling barrier, and the rhodium is the source contact, which is the substrate. And what we have is, we have a capacitive coupling of the molecule to the tip voltage. And if we now measure the differential conductance as a function of position over the molecule and as a function of applied tip voltage, we see this type of feature. And what is interesting here is actually this parabolic half-moon type shape. So what happens here is that we are starting, going from zero bias upwards, we are starting from this schematic scheme. Substrate, Fermi level, these are the filled electron states of the substrate, filled electron states of the tip, tunneling barrier 2, tunneling barrier 1. These are the molecular energy states of the molecule, and we are in a neutral state. So the molecule is in a neutral state here. As we increase the bias, what we are doing, we are pushing up a little bit this state here so that it can ionize to the substrate, and then the molecule changes in the +1 charge state. And this sudden change rearranges the energy levels, the current which is flowing through changes suddenly, and this is a little realization of such a quantum tunneling field effect transistor. Of course, only 1 by 1, and only in the intensive care unit, which is the scanning tunneling microscope. What holds the future? So again, back to function. If we go to graphene nanoribbons, actually we have very much the same philosophy as for the carbon nanotubes. Small gap, so in tight binding, actually this nanoribbon would be metallic. If you really do the full calculation, it is not the case. A small gap would go up. But this is kind of the same feature of these one-dimensional bands that we have also in the nanotubes. But if we change the edge structure, and you are now experts in band structure, you see this is very different. So this is not linear dispersion, this is not parabolic dispersion as here, but this is flat. And the reason for this is that these are electronic states which only live on the edges themselves. So this is a new property as compared to the carbon nanotube. Well, if we have this situation, we need to adapt our calculations a little bit. We need to implement electron-electron interaction. And if we do this, actually a band goes up. But the interesting thing is that there is a spin polarization. And this is now the real spin. This is not a pseudo spin, but we will have an excess of upspin or downspin on the upper edge, and the inverse spin direction, we will have a majority of them living on the lower edge. And if we can dream on, and if we could introduce a strong spin-orbit coupling, then we would get back to such kind of a dispersion relation, which again is interesting. So this is metallic type. And the interesting thing here is that the spin species and direction of motion of the electrons are now separated on the different edges. So we would have the upspin going to the right direction, living on the upper edge, but the downspin going to the reverse direction on the lower one. And again, think of backscattering without spin flip. So if this here wants to go into the other direction, it actually needs to change sides. And this is again very strongly prohibited. The only inconvenience is that graphene or carbon, being a light material, has a very, very weak spin-orbit coupling. So I would say that if there would be a wish list for further function in graphene, many, many people would wish for spin-orbit coupling to be strong in this material. So if you think about integration, and I'm coming to the end here, what are the problems? What are the big challenges? And this is a little bit exemplified in this slide here. So where these people have looked at the influence of the width of the contact on the contact resistance of transistors. And you can see here the contact resistance as a function of length, and you see that the saturation, so where the contact doesn't matter anymore, it needs very, very wide contacts of 200 nanometers. So you might say, okay, we can produce channels which are 15 nanometers, but if we have 50 nanometer contacts, we have huge contact resistance. And this is, of course, also due to the strong or to the very inert nature of the graphene. A possibility to solve this would be kind of these structures. So this is a fusion of different carbon nanotubes together, where we would have a conduction channel, and then we would open up actually the contact pad by another piece of graphene, and then we will have actually the possibility to reduce the contact resistance by making this structure larger and larger. But this, of course, also puts up the question, how do these kind of junctions behave? And also this can be investigated. So this is, again, work by Thomas, and certainly based on the work of Pascal and Roman. Here we have two graphene nanoribbons which form a vertical junction. Here we have an AFM image, and simultaneously we measure here the electron density by the current image. And now we can try to figure out what is the bonding sequence in order to reproduce this electronic structure. And you can go through all the catalog of the possible junctions, and you will find, well, the best correspondence we will have here, where all the 4 possible bonds of these 2 nanoribbons actually are closed. This brings me to the start. So here we have really the dependence of the properties of these junctions down to single bond level. So I hope that in this circle of challenges, I have talked you a little bit through. It was a highly biased selection of topics, also to position a little bit the work which have been done in our laboratory. Maybe you are convinced we have no shortage in function. There's a lot of function. Challenges are to exploit these functions by controlled synthesis, but there are approaches how this can be done. And of course, a very big challenge always is the integration of these very small materials into functional units. So with this, actually, I come to a very important part. If I'm standing here today and have the honor to be acknowledged for some of the work that I could do or to which I could contribute, this is not my work alone, of course. Many, many people have been involved. Of course, here at Empa, Roland Wittbel, Pascal, and Roland, we are now together for a very long time, but of course also postdocs doing great work, Thomas, Li Wei, of course also Hayo. I want to mention here, of course, our friends from the theoretical group, Daniele and Carlo, who are telling us what we see in our experiments, but also going back to the people at the University of Fribourg, of course Louis, and of course also Pierangelo. We have been orbiting around each other for a very, very long time, but many collaborations here for the hexagonal boron nitride with the University of Zurich, actually with the Fribourg University in Germany, and also with Helsinki for the defects on the carbon nanotubes. And certainly also a lot of people at industries with whom I had the pleasure to collaborate. So with this, of course, thank you very much for your patience. I hope I could show you a little bit what we are doing, how this is positioned, and thank you very much for your attention.
Thank you very much for this exemplary, iconic overview of many possibilities. Are there questions? Yes. Not. Wait for the microphone because we are recording it, so the questions are relevant.
About half in your talk, when you showed where you first fixed this carbon nanotube on a microchip, and where you explained the scattering of electrons at defects.
Yes.
That reminded me of sort of like a Hohlraumresonator or a reflex klystron.
Yes, of course. The standing wave, of course, goes up also with electromagnetic waves, with photons.
So you can release the energy of the system by emission of an electromagnetic wave?
No. No, here you need to see that if you have the resonator, take a klystron, the resonating modes, they exist whether you put photons in or not. The photon state exists, it is filled or it is empty. And this is the same situation. Actually, these are empty states. We are just looking at the transmission of the electrons through this resonating state or not. So this is a representation of the density of states. So there is no energy involved on this level here.
It's not charged somehow.
The transport is considered to be non-charged here, but it's a resonant transport. So we are injecting electrons, and we are looking whether we hit a level or we don't hit a level. And depending whether we are at the amplitude of the wave function, we will have a strong coupling. If we are here, we have a weak coupling. So it's like kind of a microwave probe. Think of a microwave probe measuring the amplitude of a microwave field in a resonator. This is the analogy to that. So we are kind of measuring the amplitudes of our modes in space.
I have one question that always comes back when I see transistors.
Yep.
What is the dynamics? What is the frequency? How fast can you switch these things? You showed 7,000 IV curves, but you didn't tell anything about the
speed. So I think the record is really measured. It is around 50 gigahertz. And they have extrapolated the power gain, so where the power gain is 1, up to 100 gigahertz. But these are extrapolations.
Okay.
So measured, it's about to 15 gigahertz. And maybe nowadays it's even more. I think it can, if I remember well, I've even seen 30 gigahertz. So which is not bad.
Although 3.5s are showing indium phosphide, gallium arsenide are showing similar values. I mean, from the graphene properties, you would expect even an order of magnitude faster.
Yeah,
right?
But actually, really the power, so it's really the power gain that you have, and this is of course strongly limited by the contacts.
Yeah.
So if you have the contact resistance, this is exactly what is killing you. So it's maybe not so much the dynamics of the channel, but it's really the limitations of the contacts, which plays there.
Okay. I have another thing that burns under my fingernails. Everything that we do today in our chips is top down. You cut out with lithography or whatever you have, and a lot of this is bottom up self-assembly. But defects come in quickly, and particularly when you want to make these contacts. I mean, it looks like an art to build these 3 ribbon structures together, or do they really form?
It's nature, which, so if you adapt correctly the density, so if you have a high density of ribbons and you anneal them, they really fuse together like this with very low defects. Actually, I'm not quite sure whether we see defects in the junction where they have fused together. But this is, of course, not controlled in a systematic way.
Will we be ever capable of doing it, that you can show your last charts as these companies now making a transistor based on a whatever nano ribbon it is, that is in our pockets in whatever personalized device.
So I think the printed electronics, so for flexible displays, I guess carbon nanotubes are really great.
Mm-hmm.
But for digital, so CPU-grade devices, maybe the top-down approach will come first. The bottom-up has the problem that we have material and then we need to integrate. So if we can grow them on spot, this would be a huge advantage. But the challenges are certainly very, very large. However, actually in the last 10 years, there have been progress in sorting of carbon nanotubes and placing them, which I would not have believed 10 years ago. So progress is certainly there. And what will come? We need to try and see what we get.
Okay. More questions? Yes, please.
So the center of attention was the element carbon, although it was not really outspoken. How much are you stuck with carbon as the element? Do you observe in literature that people are going to other elements or even compounds?
Yeah. So very hot topics are called the word that nobody can pronounce, dechalcogenides. So tantalum disulfide, tantalum dicyanide, molybdenum disulfide. They have a gap. Graphene has the problem, it has no gap. So if you really make a large graphene transistor, it doesn't work very well. So the on-off ratio is maybe only 10. If you use these other layered materials, like molybdenum disulfide, there you can have very high on-off ratio. The problem is, again, what is the contact resistance? So this is certainly the case. But graphene is somehow exemplary because it's stability. You can take it in air, and if you think about these structures being made out of silver, of gold, or anything, they're not stable under ambient conditions. None of them. Graphene is. So it is the material which tells you a lot. If you don't make it in graphene, it will be very difficult to make it in any other material, so to speak. But this is now opening up actually in other directions of materials. Yeah.
Well, we always say at Empa we want to be the place where innovation starts, and innovation is at the end that somebody pays the bill and buys a new device. And we all know that it's challenging to, in an Empa where we have a very flat structure, to grow in recognition and grow in responsibilities, and we only have few positions as lab leaders, and that's why we discussed internally in the directorate, can we build up a new function, kind of giving a recognition to our top-notch scientists or engineers, and with that I mean people that have really a leading role scientifically, as shown today, or also being the person to go to in an industry, in a field. We have 5 research focus areas, and some are closer to transitioning to industry, and some are closer to basic science. And we want to give such people that are known for their work, whatever it be, scientific, basic science, or making an impact to an industrial area. We want to give them a little recognition. And that's why we have created this position, Distinguished Senior Researcher. And we have a couple of people applying, and we went through a process. And this lecture was, for me, the first one where we had one of our colleagues that we could recognize with this. And from that perspective, I'm really happy that with Oliver, we have a person that has made contributions in very many fields. Of course, a lot has to do with carbon, but I know that he has done more than that, and a lot has to do with tunneling, scanning probe, IV characteristics, and all of that. And that's why we have created this Distinguished Senior Researcher little recognition, and he's the first one that I'm having the pleasure to hand it over.
So much.
Thank you.
Thank you.
And congratulations to this. For me, it's also a person that I can sometimes call, and my colleagues as well, because we sometimes have challenges that we don't know how to solve. So it's not only that you can just do nice research. Every now and then we will bug you and will introduce you to other challenges. But for the time being, I was very delighted to learn this overview, what we are doing in this field. And I know it's even more than that. It's very complex. But now, after all that, we have a little apéro outside. And you can ask all the questions to Oliver that he didn't answer or you didn't dare to answer in the meantime. And let's share a little drink together outside here of the room. Thank you once again for your contribution.
Thank you very much for the appreciation. Thank you.